Houston, Texas. Today, being a holiday, a rodeo, one of the aspects of America's recent past, is taking place. In the Houston of Apollo 11, of the Armstrongs, of the moon landings, thousands of people, young and old, are enjoying the sight of the cowboys, the steers, and the lassos. Houston today is taming not only the world of outer space, but also the steers. In the city where man's future is being made, or at least a part of it, this movie does not document either the world today or even the present, but a past which we are accustomed to live only through the various reconstructions provided by a movie. Old and new in Houston live together side by side, and it's not quite sure if it's the old that is in a hurry to pass away, or if the new is in a hurry to be born. But in Houston, side by side with Sunday's enjoyment, which really only exists at the circus or in a movie program, there is Rice University with its students and scientific research that is preparing a future for which we do not yet know today if it is a case for hope or despair. In any case, man's future will be science's future. At Rice University, scientific research is applied in different fields and in different studies, from nuclear physics to electronics, to astronomy, to anthropology, to medicine, to ethnology, etc. Scientific knowledge here at Rice University finds a fertile soil.
Tape recorder behind us is the recorder we use when we're recording thunder. This whole unit goes inside the truck when we go out into the field to record thunder. I'm playing back some of these thunder records now, and you can see the pressure variation on the oscilloscope up there, and you can actually hear it. We have part of the sound coming through that speaker there on the other side.
And you study much more the thunder than the lightning, I think.
Yes, this is, we got started in the business interested in thunder because we thought it might be related to some ionospheric phenomena that are associated with thunderstorms. But when we started investigating thunder, we found out how little was known about such a common, everyday type occurrence that we thought it would be worthwhile just to study thunder for itself. So, the last 3 years, we've been concentrating on understanding the thunder signal. It's a very complicated, as you can imagine, signal. We have several examples of it here that you may want to look at. But in order to study this...
And what do? You chase thunders?
That's right. That's right. We have a truck, a small truck, filled with the tape recording equipment. And we use very low-frequency microphones. Here's one of our microphones, special low-frequency microphone that we think gets all of the sound produced by the thunder. It actually sits on the ground sort of like a mushroom. And this will record the sound variation.
And how many microphones you use?
We have 3 of them.
3.
An array of 3 of these low-frequency microphones. Then we have a high-frequency microphone to give us a very broad...
And to what distance you put the microphone?
About 30 meters. And
because the speed of the sound is very low. Huh?
The speed of sound is slow. It's 340 meters per second. So, in a tenth of a second.
Nothing in comparison of the light.
Oh, very small compared to light. And it takes about a tenth of a second to get across the microphones if it's traveling parallel. So with these 3 microphones and our tape recording equipment, we chase our thunderstorms, so to speak. We get in our truck and go out into the country where there's very little city noise. And we set up our microphones and start recording the thunder. And we've been doing this now for about 3 years. This past summer, we really got some good experience with our truck. Prior to last summer, we had done all our recording near Houston. This past summer, we took the truck and went from Houston to Roswell, New Mexico, and recorded thunder. And then we moved to Socorro, New Mexico, to a observatory that's operated by the New Mexico Institute of Mining and Technology. It's situated up on top of a mountain, the Lanier Laboratory. Its altitude's 10,800 feet, so it's a pretty high peak. We studied thunder there for a while, then we moved the truck out to Tucson, Arizona. They have a reasonably high elevation, but in a
thunder, the sound, the same thing in a mountain than in a flat region?
Basically, it's the same. There are a few...
But what created that grumbling sound of the
rumbling thunder? Well, I think our research here has really shed some light on the nature of this rumbling thunder. Prior to our investigations, all the theoretical work that had been done in thunder, building a model to explain thunder, the scientists concentrated on simulating thunder with a very long straight line from the bottom of the cloud to ground. Just a straight line. And when they predicted the sound coming from this straight line, it was just one little bang, or one big bang, I should say. A sound very similar to a supersonic boom from an aircraft. Well, this is not what thunder sounds like.
Absolutely.
And in fact, the values they get for this sound wave were all wrong. They didn't match up with what you could measure. Well, what we have done is to study the effects created by the tortuous lightning channel. This is the channel with all the little wiggles in it. And these irregular... I have some...
Is irregular like the lightning?
That's right. Here are some photographs of some lightning flashes out in Tucson last summer. We have the thunder recordings to go with these lightning flashes. And you can see by looking at these that it's very obviously not a straight line.
Not sure.
And so we built our thunder theory around a better model of what the lightning channel is like. Now, I have an enlargement of this area of the photograph here, when you can see these little wiggles and tortuous pieces of the channel more clearly. There's another important thing about this photograph that I can point out. And that's the difference between this lightning channel and this lightning channel.
Mm-hmm.
If you look at all the branches coming off of this lightning channel, they all branch downward toward the ground. If you look at this lightning channel over here, you see that the branches it has are branched upwards.
Then why that?
Well, this lightning channel, the lightning flash, started at the ground and went to the cloud.
It can happen also then?
Yes.
Is it very often happen that?
It doesn't very often happen in a natural situation like this. It very frequently will happen from tall buildings like the Empire State Building.
I see.
And Professor Berger's laboratory in Lugano, Switzerland, they have a tower on top of a mountain.
Mr. Rossellini, this is a circulatory system simulator which has been developed here in this laboratory. And one of our principal activities here is the development of an artificial heart. Now, that is obviously a long-term, very difficult problem, but we have been working on it now for about 5 years, and we have developed some very interesting devices which do show a good deal of promise. Now, let's just go through this circulatory system simulator. This simulates the one side of the heart. This flexible reservoir here is at approximately atmospheric pressure, much as is the atrium, or the upper chamber of the heart. Then this chamber here actually does the pumping, so you could say it simulates the more muscular chamber of the heart, the ventricle. And you can see the valves opening and closing, and you can see that the flow is driven by a diaphragm. Now, this diaphragm is driven by a pressure pulse from this pulsing unit, which was also developed here at Rice University. The flow comes out of this simulator of the ventricle, and it comes around to this flexible reservoir. Now, this reservoir acts very much as the aorta in the human body. The aorta is a large, flexible reservoir, and because of its flexibility and its ability to contract, your blood pressure does not drop down dramatically when the ventricle is not pumping. Your blood pressure, as you may know, drops from about 120 millimeters of mercury down to about 80 millimeters of mercury mainly because of the action of the aorta, this flexible reservoir. Then the flow comes on around. We have this clamp here, which is a restriction on the flow, and this simulates the body's capillary bed, this pressure drop in this restriction. And all of these elements are adjustable so that we can tune this thing, so to speak, such that we do simulate the flow rates and the pressures that are seen in the human circulatory system. The flow comes on back around. This large device here is just a meter so that we can tell how well the unit is performing. Then it comes back to the atrium. Now, of course, if this were simulating the complete system, we would have two of these loops, one for the system and one for the pulmonary side, or the lungs. Now, most of this work on design of these devices and development of these devices has been done by Professor Akers, who is in this laboratory, who's not here today, and by Mr. O'Bannon. Now, Mr. O'Bannon is our chief mechanical design engineer, and he has personally done much of the design work on this equipment. At this time, I'm going to ask him to show you through a little dye injection experiment how the flows go in this device. Bill, if you'll just come in here and show Mr. Rossellini, please.
Now, in just a moment, I'll inject dye into the atrium. It will flow through the mitral valve, into the aorta, out through the aortic valve, and through the aorta, and then into the peripheral system. we saw the dye injection a few minutes ago move through the ventricle into the aorta, in turn it went to a capacitance box which simulates the elasticity of the arterial system. Then through a resistance which simulates the capillary bed in the body. Then through a rotometer, which is a flow meter that tells us how much flow in liters per minute that we're flowing. Then back into the atrium and then to the ventricle and around and around. We are monitoring aortic pressure on this oscilloscope, and the unit that is powering the artificial heart is below, as we see the two dials, and that tells us the pressure, the systolic and diastolic pressure that this system is being operated at, and the two control knobs that we can vary these pressures for whatever condition that we want to simulate in the mock circulatory system.
This is an original pattern that is all hand waxed, and from this we make our first silicone mold, which is this rubber material. From this mold we can produce as many times as necessary, and then we remove our wax pattern, which will come out about like this, and this in turn is invested in this flask. We remove our mold, our pattern from this mold, and then this flask is then placed in a balling water bath in the lost wax technique. The wax is balled out. Then the material is replaced with this acrylic. This is the finished product that comes from the flask after our flasking technique is completed. This is only one part of the heart, one side. As the pieces are made, they're assembled in this form.
Well, I'm not an experimentalist. I'm what's known as a theoretical scientist, working mostly with mathematical tools to understand properties and scientific principles. And I think a theoretician, at his best, is somewhat like a caricature artist. You know, a caricature artist doesn't try to give a realistic picture, paint every detail, but pick out a certain feature which he feels emphasizes the subject matter and the idea. In the same way, a theoretician would try to look at a physical situation, not produce all the numbers that one would measure in the laboratory, but try to pick out the essential idea behind the physical phenomena, or what he thinks is the essential idea, emphasize that in a model, and then see whether he can understand the things in terms of the model. And I think an example would be two molecules that ordinarily we know they repel each other because we have difficulty compressing solids and liquids. So we know there's a repulsive force between molecules, and you'd like to understand what does that repulsive force do? Where does it play an important role? And so you'd make up a model. It might be a model of hard molecules. That is, you wouldn't allow them to penetrate at all. They would be infinitely hard. Now, this is not any realistic molecule of that sort, but you, like the caricature artist, you've overemphasized the feature. You've done it quite often for mathematical convenience, that is, it helps you in your mathematical analysis, but quite often you've done it like a caricature artist does to see whether you can see some general underlying thing that that one feature conveys or that one feature illustrates. And so that's, I think, quite often what a theoretician does when he's at his best, when he's really trying to explain scientific principles. Of course, he also has to, from time to time, really try to make a detailed theory to calculate numbers which then can be compared with experimental data to make sure that at least there's consistency between his ideas and what is really going on in nature.
With that system you can open the road to the experiment or something, or to comprehend better what...
That's right.
It's a general orientation, or...
Yes, I think what
more than that.
Yes, what one would like to do, experiments, of course, play a very important role. One would like to look at experiments, organize them, rearrange them in different ways, look at them from different points of view, and then perhaps hopefully get a good idea, Now, what is it that's really causing this phenomena? How can I understand it better? What is the most important feature behind it? And then to build yourself a model. Then you go off and you build yourself a model analogous to this caricature portrait you might paint, which just has built into it these features which you think are most essential. And then you try to analyze that model. That is, you try to do the mathematics that's involved to calculate out what the results would be, and then see if your model produces something which is analogous or does resemble what was observed in the experimental data. And if you can achieve that, then you've done a successful job as a theoretician.
You were at Los Alamos.
Yes. When I was a student, and in the early days in 1950, I used to spend my summers at Los Alamos. And it was then that I had an opportunity to meet Enrico Fermi, who, of course, we all regard as a very great scientist. And in fact, he impressed upon me something he told me at that time about the ability to convey scientific ideas. He said, a good test of whether you really understand what you're doing, understand your scientific ideas, if you can explain it to a person without technical knowledge. I think he really believed in that at the time you couldn't explain something was the time you really didn't understand it. When you at last had an understanding and a really deep insight, then you could convey the idea to anybody. It didn't require any real technical knowledge to tell them what you were doing. And he always used to teach the introductory physics course at the University of Chicago, and always claimed that he enjoyed it, and that was the thing that he felt it was important to do, because it was important for him to test and be able to see whether or not he could explain his ideas to people who had not had the technical training or the technical background. And I've often used that. Very seldom have I really been successful. Quite often I find myself using scientific jargon or mathematical language, forgetting that I've learned it through years of practice, and the person I'm talking to doesn't know anything about it. But I always come back and I always think of what he said.
This is exactly what I hope that can be done through film.
Yes, and I hope that's successful. I've tried myself quite often to explain ideas, and I've often floundered around and been only successful part of the time, that I realize it's a very difficult problem. And I'll be very, very pleased if you are successful in conveying even part of the idea.
Let me, that you must be successful.
Yes, all right. Or if this technique is successful,
yes,
let me put it that way. If this offers a new avenue, a new road to get across some of the ideas, if it turns out that it is somehow, for some reason, more successful than going in lecturing to students or giving formal discussions, then I think it will be very worthwhile. And it's not only a matter, I believe what Fermi said quite often, it's not only a matter of conveying to the general public what we are doing, getting across the ideas of what goes on in science, but I think we can help ourselves in doing it. Because I think if we have a means of doing it, the very fact that we would make an effort then to explain what we're doing would help us in our ideas and our understanding, because it would help us clarify our points, it would help us sharpen them, make them more concise, make them more understandable, and in making them more understandable to somebody else, they become more understandable to us. I think that's true in everything, as you try to explain it.
This is a gamma ray telescope that searches for radioactivity from the stars. It's different from the optical telescopes that you may be more familiar with, even though it looks a little bit like them. Optical telescopes use lenses and mirrors. This thing uses scintillation counters, just like you use for prospecting for uranium. The only peculiar and special feature of this one, which was built here, is that unlike most scintillation counters the prospectors use, this one is very directional and will only look in the particular direction in space that we aim it at. It is then sensitive in the range of wavelengths that are characteristic of radioactivity. So what we're doing is we're looking for radioactivity from this place in space. The machine that does the aiming is this gondola, which points the telescope. The telescope is
slung from the balloon in this gondola, in this cage work part of the gondola. And as you can see, it's free to rotate in azimuth. It follows the stars by virtue of the fact that it is pointed north along the Earth's magnetic field lines and is free to rotate to follow the stars once every 24 hours. We send commands throughout the flight to update the latitude of the balloon, enabling the upper portion of the cage to move.
This part is really the heart of the experiment. It is called mass spectrometer, and it's used to measure the gases that we have extracted from the lunar sample on that side. We can measure with this both the total amounts of gas and their isotopic composition, which gives us a lot of information on the sample. Now, this portion here actually which is inside this oven, is where the samples are melted. Now this here is the part of the system where the samples are melted and where the gases are extracted. The actual melting takes place in this furnace here, where the sample is dropped into this metal crucible. Now, if you come over here, I can show you more closely what this furnace looks like. This is a furnace very much like the one that I have shown you earlier. Inside it is a metal crucible, like this here, which is heated from the outside. The sample is, as I've told you earlier, is wrapped in this aluminum foil, and it is loaded in one of these side arms from which it can be dropped into this crucible. Now then, the coil which you have seen on the outside fits right around the furnace in this manner, and that is the way in which we heat the crucible to rather high temperatures. Now we're really in the most exciting part of the experiment, because now the results are coming in. What we're looking at is a write-out of the measurement of one of the neon isotopes. The mass spectrometer is operating, and the ion beam, about which we will talk a little later, is falling on the detection part. And as the ion beam comes on the detector, the current and therefore the voltage increases, and that is what makes the pen go up. And ultimately, of course, the intensity of this ion beam is given by the top of this peak. We can in this way write all the isotopes of a given element, in this case of neon, and we can in this way find out how many of each of these isotopes there really is in the lunar sample. Now, I can tell you that when we were doing these experiments with the lunar sample, we would do, say, 2 experiments, and then we would make a theory, and then my co-worker and I would bet on the results of the next experiment, and I lost a lot of money that way. And of course, after the 3rd result, we would make a new theory, because the old one was wrong. And that's the way we operated.
And how you here now, for example, is the analysis of neon.
Yes.
And you can analyze also all the kind of things.
Yes, I can analyze all the inert gases, helium, neon,
But
argon.
they are all together. You can divide those gases from the sample.
That is done first in the chemical part, where I have a little tube filled with charcoal, which is cooled to liquid nitrogen temperature. And at these very low temperatures, the heavy gases, argon, krypton, and xenon, are absorbed on the charcoal, whereas helium and neon go on. But also the instrument itself helps in this separation in the following way. In this portion of the instrument here, we bombard the gas with electrons. Now, from time to time, an electron hits an atom and knocks off an electron from the atom and makes it positively charged. Now, the remainder of this portion here, where you see all these metal plates, acts like a cannon. It takes these ions and shoots them into this tube here of all the different gases all together. Now, these ions come into a magnetic field. This is a magnet with the North Pole and the South Pole. And in that magnetic field, they are forced to travel on a circle. And the light ones travel on a circle with a small radius, and the heavy ones travel on a circle with a big radius. So what came into the magnet as a mixture of all the masses now comes out as separate individual little beams, each of one given mass only. And by changing the magnetic field, and that's actually what we were doing here, I can pick out one of these little bundles and throw it on the detector. And so both by chemical means and by the mass spectrometer, I can measure all these gases separately. This is the safe where we keep the samples so that they cannot be stolen, although I don't know what anybody would want to do with it. Here I have a number of bottles with parts of the sample on which we already have done some experiments. And in this pillbox, I have the sample which will be measured upstairs. And then this is really a bottle that has some history to it. This is the first bottle in which we got the sample at NASA. And we took it to Rice University, my collaborator and I, and we couldn't see anything because it's plastic. Then we opened it up and took the inner bottle out. We still couldn't see anything because it was wrapped in aluminum foil. And I will never forget this. We took the aluminum foil off and we saw this black dust. And we said, "Gad, look at the dirt." It looked exactly like dirt, you know. And you had been preparing for it for 2 years. And maybe you thought you would see a diamond or something very precious, and it was just like anything you pick up in your garden or on the street. But despite that disappointment, we had very exciting weeks afterwards.
And we can see something on the microscope?
Yes, we can have a look at some of this material under the microscope.
We are at the 430 megahertz transmitter console. This is the major transmitter for the observatory. It is used by both the ionospheric and the radar astronomy groups. The various controls here are to set the pulse width in microseconds. On this control, we determine the pulse repetition frequency by this control. On the oscilloscope, we can see the power delivered by the transmitter. There are two large klystrons, and we can get a total of 2.5 megawatts. The various dials are to protect in case of any failures, and the transmitter will automatically shut itself off. To my right is the other transmitter that is used at the observatory. This is the 40 megawatt transmitter. It is used in one experiment to heat the lower ionosphere. Send up pulses with this transmitter to heat the electrons. Then with the larger transmitter, we observe the temperature change of these electrons. The transmitters can be used to bounce signals off of the Moon, Mercury, Venus, Mars, possibly in the future Jupiter, and there was even an attempt to bounce signal off the Sun.
Okay, we're now standing on the feed arm of the observatory, an arm which rotates to allow the antenna to point at different regions of the sky. The sound that you hear in the background is that of the transmitter. It's chirping at different frequencies and probing through its echoes the ionospheric densities above us. The transmitter is situated down in the main building, and the power comes up a waveguide along the catwalk, up into the structure above us, down through a circular guide, and into a slotted waveguide section that runs into the line feed, a 96-foot line feed that's somewhat below us. That feed, in turn, is on a carriage house which is able to move out along this feed arm so that it can cover an angle of from 0 out to 20 degrees, and through the rotation of the feed arm cover a 40-degree sector of the sky. When the feed was originally constructed, we're now standing on about 550 tons of metal, so that we're just about as solid as if we were standing on the ground. The basic triangle above us was constructed on the ground and raised very slowly by drawing back on support cables connected to each of the three towers. The tallest tower is about 460 feet, and we are about 500 feet above ground right now. After the main triangle was set up, the circular guide was constructed in place, then this feed arm was constructed on the ground and raised, and lastly, the carriage houses containing the equipment and the antenna feeds were installed. See, the experiments that we do include work on the ionosphere, generally pointing straight up and measuring densities and temperatures and compositions. The ionosphere is the region of the Earth's atmosphere that is broken up into charged particles, electrons and ions, by the solar radiation during the day, and then slowly recombine at night to return to a neutral state. The detailed variations of these densities are under study at the observatory in efforts both to understand why the ionosphere varies as it does and hopefully to be able to better predict how it will behave at various times and under various conditions. This is important for a number of aspects, particularly for communication purposes. When one listens to an AM radio or communicates at frequencies below about 10 megacycles up to several tens of megacycles, the communication in the absence of space satellites, which is a relatively new advancement, takes place because the ionospheric layer exists and one has the radio waves reflecting back down off of it. It is present above us from about 50 miles up to several hundred miles, depending on how you wish to define its termination point. The fact that we are able to move the feed also allows us to track a large region of the sky and make astronomical observations. The
radar work is done on the planets, and we are able to transmit a pulse, wait for several minutes to the order of a large fraction of an hour for the echo to come back, and then receive the echo from the planet, and on the basis of its characteristics, actually do mapping of the moon and certain features of the planets. Work done at the observatory has shown mountains on Venus and has determined the rotation rate of Mercury as being 3.5 as opposed to 2.5 rotations, or 1.5 rotations rather than a planets. Work done at the observatory has shown mountains on Venus and has determined the rotation rate of Mercury as being 3.5 as opposed to 2.5 rotations, or 1.5 rotations rather than a synced orbit around the sun. The work that we do in the ionospheric area includes not only backscatter probing with the antenna, but correlating this information with a number of other emissions from the sky which tell us about the neutral constituents. The backscatter radar tells us primarily about the electron components.
And back of us now in the hills we have a small hut with 3 photometers. These will look at various air glow lines. A couple of very prominent ones and of interest are oxygen lines, one in the red and one in the green. From the red line, if one measures the width of the line, one can obtain the neutral temperature. And this is done often in conjunction with the backscatter. And there has proved to be very good agreement between the electron temperatures and the neutral temperatures at a given time at night when one would expect this agreement. Thus, each method of measurement supports the other as to its accuracy. Also, in the early morning, there is an enhancement.
Console and structure behind it, We're sitting in the control room of the Arecibo Observatory. In this room, we have the radio astronomy receivers and the control console for the pointing of the antenna. The antenna, as you can see, is a big structure behind us, and this console turns with the associated computer system, controls the motion of the azimuth, arm, and the 2 carriage houses. Greenwich Mean Time is displayed on this clock to tell the computer where the Earth is, and we put in the coordinates of the celestial object we wish to view here. Then the computer automatically points the antenna at the position in the sky where we wish to. Also in this room, the radio astronomy receivers work to give us this an electrical signal out of the radio source.
What we're doing now is that this chamber here is a vacuum chamber that we calibrate the instrument in. The instrument, of course, can't work in atmosphere. It has to work under vacuum, and so therefore calibration has to be done under vacuum. And we're seeing here essentially the end result of what I would call the third phase of an experimental program such as this. So the first phase would be, of course, an initial concept of an instrument. And the second phase would be building a prototype and seeing if it works. And the third phase would be building a final flight-worthy unit and finally calibrating it so that you can relate the numbers, essentially, that come out of the unit to various geophysical phenomena of interest. And now we have finished this third phase, this calibration phase of the instrument, and we are now preparing to bring it out of the chamber.
Excuse me, what is that instrument that is using now?
Well, the instrument itself is an instrument for detecting charged particles, electrons and protons, atomic-sized charged particles. Now, the process you're seeing here is just a very careful sort of checkout. These are we have to be very careful with cleanliness and handling and things like this. And so there's certain established procedures dealing with flight instruments of this sort. And so as I was saying, this charged particle detection instrument will now go from here, from our calibration facility, to be put with the rest of the instruments on the ALSEP package, the Apollo Lunar Surface Experiments package group. And of course, then the next phase will be Apollo 13 launch, transporting it to the moon, deploying it on the moon by the astronauts, just setting it on the surface of the moon. And then we'll be ready for really the last and final phase, which is gathering of the scientific data and working with this data and trying to, well, the eventual object, of course, is to try to understand more about our own environment and more about science and more about physics. Now, as far as the mechanical task here, we, of course, have to disconnect the instrument. You notice the procedures here, the handling procedures. We are being, as I pointed out, you have to be quite careful with these things. This entire room is designed to be kept quite clean.
But after that, you do another operation of cleaning, perhaps, for the dust or things
well,
like
that.
Of
course, the object is to keep anything from happening to it. I mean, it's the sort of instrument that a speck of dust in the wrong place, or something like on the order of a grain of sand in the wrong place, could seriously affect the operation of the instrument, and that's why we're in these sort of things. Now, we can come over here and have a little better look. Now, the instrument will be placed on the lunar surface by the astronaut. It will be leveled with a standard sort of bubble level, just like you see in a carpenter's level. It will be aligned using the shadow of the sun as a reference. And then, after the astronauts have left the surface of the moon, and any dust or exhaust gas from the lunar module have settled back again, and the environment is once again clean, a cover here on the top surface, known as the dust cover, will be commanded from the ground to roll back and expose the actual apertures of the detectors to the lunar environment. And that's simply done. See, the dust cover is now on, and on a command from the ground, very rapidly, the cover will flop back like that, and now the top surface of the instrument, containing one detector here and one detector here, is now exposed to the lunar environment. And the instrument starts sending back data to the Earth, where it will be received, translated, and brought here to Rice University for final processing and analysis.
You say that's the result of the work that you have done in Iran.
Well, I've been working there for about 10 years, and I've been particularly interested in the origins and development of agriculture. Up until about 10,000 years ago, all the people on Earth were hunting and gathering, and about 10,000 years ago they began to use domesticated plants to supplement their wild diet. And the excavations that we've done in Delaran have documented about 4,000 years from the very beginnings of agriculture up to the time they had the kind of agriculture that they do today, which is with bread wheats and barley, and where they have cattle, sheep, and goat domesticated. So the excavations have been to determine when agriculture began and what its development was and what effect it had on the
And
people.
now you can date it so precisely.
Well, we date it because we can date the carbon that we find in the sites. We find that people made fires and they left charcoal behind, and we take the charcoal and put it in bags and bring it back, and the laboratories can date the radioactive carbon isotopes that remain in the carbon. And on the basis of that kind of dating, we have found that agriculture began about 10,000 years ago. And it was just a very, very small beginning that they had. They were mostly hunting wild animals. They were mostly collecting wild plants, alfalfa and various peas and beans. And they were also harvesting the kind of grasses that later became domesticated into wheat and barley.
When you say domesticated, you think that those plants, they transform because they were used by the man, or the man influenced in the transformation of those kind of plants? When you say domesticated, what you mean by that?
Well, domesticated in this case means that people began to plant them deliberately and to move them from the places where they originally grew. The plants originally grew up in the mountains of Iran, and they moved those plants, they moved the seeds down to the plain of Delaran, where I've been working, and actually planted them, harvested them, and then planted some more. And in the process of this, they began to select the plants that produced the biggest seeds. And out of that developed a hybrid kind of plants that we have today, which grow much larger and more densely than the wild ones did. And that's what we mean by domestication.
Yes.
It's a gradual change of the wild plants through the tending by man. People took care of their reproduction by selecting certain kind of grains and putting them in the soil and harvesting them. And they lost many of the characteristics that they had when they were wild. For example, a wild wheat breaks very easily so that its seeds will scatter. When the wind blows or when an animal walks by, the seeds fall off on the ground. Well, that's very good for a wild plant, but it's not good for a domesticated plant, because the man who goes out with a sickle and wants to cut it does not want the seeds to fall on the ground. He wants to bring the whole thing back. Well, in cutting, they began to pick the seeds that stayed with the plant, that did not fall off. And gradually, the wild-type plant where the seeds fell off was replaced by a domesticated plant where the seeds did not fall off. It's a change in the structure of the plant eventually, because people selected by gathering certain kinds. They emphasized that characteristic, and eventually all of the wild ones disappeared from the wheat fields. And then people had to think of ways of threshing the grains, how to get the seeds free from the plants. And they began to use tools like this. A wheat seed is very difficult to eat. It's very hard. So what they did was to invent a stone that they could grind it on and crush it. And they began to do it this way. And then they made flour, and the flour could be used mostly for porridges. And for that purpose, they needed to have some kind of a bowl or container that they could soak it in water or something. And they began to make pottery. The first of the pottery that they made is like this. It's a very fragile, soft pottery, but it would contain the flour, the seeds, and liquid, and they could let it ferment in there, and they could let it soften up. The early pottery wasn't very good for cooking, but it could be used for soaking. Interestingly enough, maybe this was the way beer started, because they were using barley. They let it sit in pots and ferment it, and then they could drink it. It was only after about 2,000 years of experimenting with domesticated plants that they developed a variety of wheat that could be used for making bread, because it has to be a special kind of wheat. So the early ones were used mostly for porridge or for beverages. Now, at the same time they were domesticating the cereal grains, they were also working with animals. They had the sheep and the goats. Now, of course, the people were hunting the wild ox, and they were hunting gazelle, they were hunting a kind of wild donkey, but they were also keeping sheep and goats, beginning to keep those in herds around the houses. Now, one of the problems they had was to cut up some of these big animals they had, and they had a very crude kind of stone chopper that they used for that purpose. It's just a pebble which they've broken it, and they can use it for chopping. It's a very simple device, but that's what they used. think, though, that for the domesticated animals, mostly they were keeping them for their milk, and later they used the sheep and the goats for their wool and for the hair, so that they could make tents and clothing and things of that kind. The domestication process went along about the same way as with the grains, and by 5,000 BC or 7,000 years ago, we have animals that are the same as they are today, the sheep and the goats and the cattle, all being used, and cattle began to be used to draw the plows so that they could plant more land and get more under cultivation with the same number of people. It was a very important change for them when they began to use draft animals.
And the plow was invented very early.
The plow seems to have been invented somewhere maybe 6,000 or 7,000 years ago. We don't know exactly when they began to use it, but somewhere around then.
Yeah, in Luxor, in Upper Egypt, in 1945-46, the fellahin, digging in a cemetery, discovered 13 codices of our ancient books, discovered in, written in the Coptic language, which have been now recognized to be 4th century translations of 2nd century documents. After many false starts and a lot of diplomatic problems, these manuscripts are now being made available to the scholarly world for editing and publication, translation for their study. Some preliminary studies have already been made. We know, for instance, what the collection consists. It consists of material that belongs to a group who are known as, are called Gnostics. The material is divided between non-Christian Gnostic literature, perhaps of a Jewish origin, Christian Gnostic literature, some material that is really more ethical in character. For instance, there's a copy of the Sentences of Sextus involved. I'm a member of an international team of scholars who is engaged in editing and translating and publishing the total, complete collection of documents. Our headquarters is in Claremont, California, at the Institute for Antiquity and Christianity. My assignments in the publication project is 2 documents in Codex 5, the Apocalypse of Paul and the Second Apocalypse of James. Now, I have already written, made a translation and interpretation, analysis of the document, and have sent it to Germany, to Hamburg, where it will be translated into German and published in Germany by Reich Verlag. This is the manuscript, the English form. Now, I am at the moment working on the Second Apocalypse of Paul, and preparing a translation for the publication of the Institute for Antiquity and Christianity, and also for publication by the German Archaeological Institute in Cairo. The next most important thing that needs to be done, and in fact will be done as soon as the political situation in the Near East permits, we're going to the site where the documents are supposed to have been found by the fellahin, and see what we can discover about possible original owners of this collection of materials. We'll look for possible remains of possible dwelling sites, if perhaps there were a community there. And we will also make some excavations in the cemetery with the hope of identifying the type of community that lived there. And of course, we would always be open to the discovery of more manuscripts. But the The scrolls themselves have not, or the codices have not received the attention that they deserve because they were obscured by the discovery of the Dead Sea Scrolls, and because they could not get into the public view for various diplomatic and scholarly reasons. But they are equally as important. Whereas the Dead Sea Scrolls throws light upon the type of Judaism out of which Christianity came, these scrolls, having originated in the 2nd century, are going to throw important light on early Christianity, which the period is very obscure in spite of all the research that's been done on it, in spite of considerable literature we have. But heretofore, our main information about the Gnostics was provided by church fathers of the Orthodox caste, who always portrayed the Gnostics as rather stupid heretics and immoral. And we are discovering that this is not the picture from the Gnostics' own writings. In addition, some important information is being given about the transmission of the early Christian literature, like, for instance, the collection of sayings of Jesus. We have found in the Nag Hammadi collection a document which consists of 114 sayings of Jesus, one after another, many of which we already have in our Gospels, but many which we had not had before. This teaches us something about the way the material was transmitted, how it developed and grew under different locations. And, for instance, the documents that I'm working on, the Apocalypse of Paul and the Apocalypse of James, sheds light on how these apostles were understood in a context other than the Catholic Church or the old Catholic Church orthodoxy. And in addition to that, fills in some of our gaps in our knowledge of the actual history of these apostles. For instance, the Apostle James, we have in the document I'm working on a description of his martyrdom in Jerusalem. We already knew about that, knew about the martyrdom in Josephus. But here we have another description of it, and so it supplements, fills out our historical knowledge. We also are now discovering that the Apostle James was a favorite among the Gnostics, whereas before we had thought that he was the favorite only in a narrowly Jewish kind of Christianity. And here he turns up as an important figure among Gnostic Christians. So I think the library deserves the best that the scholarly world can give it. And the importance of our project is that finally the entire scholarly world will have access to both editions of the text with English translations and brief introductions. They're not going to be thorough, the last word, because our intention is to get them to the scholarly world, so all the scholarly world who's interested can participate in them.